It's plausible that the lighting and convenience outlets are wired to a 240-volt circuit source from the 480-volt system using a wye-delta transformer. In this setup, the transformer's primary side connects to the 480-volt system while the secondary side feeds the 240-volt circuit. The 240-volt circuit's grounded conductor is tied to the transformer's neutral point. A measurement between the grounded and hot conductors in the 240-volt circuit might reveal a reading of 216 volts. The reason for this is that the grounded conductor doesn't truly sit at ground potential, instead hovering around 120 volts beneath the hot conductor's potential. This voltage reduction happens because the transformer is a step-down type, lowering the voltage from primary to secondary sides. Power tools and lighting designed for 240 volts should function without issues at 216 volts. However, it's vital to recognize that the 240-volt circuit's grounded conductor isn't genuinely at ground potential, necessitating safety measures to prevent electrical shocks when working with this circuit. The grounding system in electrical circuits is designed to provide a low impedance path for fault currents to return to the source, tripping a circuit breaker or fuse and preventing electrical shock hazards. In a properly grounded system, the grounded conductor, often referred to as the neutral, is connected to earth at the service entrance and at various points throughout the distribution system. This connection to earth ensures that the grounded conductor is at or near ground potential. When a fault occurs, such as a live wire coming into contact with a grounded metal enclosure, the fault current flows through the grounding system back to the source. This high current flow causes the circuit breaker or fuse to trip, quickly disconnecting the circuit and preventing a dangerous voltage from being present in the enclosure. However, in some situations, the grounded conductor may not be perfectly at ground potential. This can occur due to a variety of factors, such as voltage drop along the conductor, impedance in the grounding path, or the presence of ground currents. In these cases, the voltage between the grounded conductor and earth may be non-zero. This voltage difference can be particularly noticeable in circuits that are derived from a transformer, such as the 240-volt circuit described earlier. In a wye-delta transformer configuration, the primary side of the transformer is connected in a delta configuration, while the secondary side is connected in a Y configuration. The neutral point of the wire winding is connected to ground, providing a grounded conductor for the secondary circuit. However, the voltage between the grounded conductor and earth may not be exactly zero due to the factors mentioned above. This can result in a voltage reading of 216 volts between the grounded conductor and a hot conductor, even though the circuit is nominally 240 volts. It is important to be aware of this potential voltage difference and to take appropriate safety precautions when working on electrical circuits. Always use a properly calibrated voltmeter to verify the voltage levels before working on any circuit. Wear appropriate personal protective equipment such as insulated gloves and safety glasses, and never assume that the grounded conductor is at ground potential. If you are unsure about the safety of a circuit, consult with a qualified electrician. Understanding the grounding system and the potential for voltage differences is crucial for ensuring electrical safety. By taking appropriate precautions, you can minimize the risk of electrical shock and prevent accidents. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, including grounding requirements. It is important to consult the NEC and follow its recommendations to ensure that electrical systems are installed and maintained safely. For example, NEC Section 250.24 covers grounding requirements for separately derived systems, such as those using transformers. This section specifies the requirements for grounding the neutral point of the transformer and for bonding the grounding electrode conductor to the grounding electrode system. NEC Section 250.166 provides requirements for grounding of systems of 1000 volts or less. Always consult the latest edition of the NEC and any applicable local codes to ensure compliance with all requirements. Grounding electrode conductors are used to connect the grounding electrode to the equipment grounding conductor, the grounded conductor, or both, at the service equipment or at the source of a separately derived system. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the ungrounded service conductors or the equivalent size for parallel conductors. The grounding electrode conductor must be made of copper, aluminum, or copper-clad aluminum, and must be installed in a manner that protects it from physical damage. The equipment grounding conductor is used to connect the non-current carrying metal parts of equipment, raceways, and other enclosures to the grounding system. This conductor provides a low impedance path for fault currents to return to the source, tripping a circuit breaker or fuse and preventing electrical shock hazards. The size of the equipment grounding conductor is determined by NEC Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. The equipment grounding conductor must be made of copper, aluminum, or copper-clad aluminum, and must be installed in a manner that protects it from physical damage. Bonding is the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. Bonding is essential for minimizing the risk of electrical shock and for providing a low impedance path for fault currents to return to the source. NEC Section 250.92 covers bonding of metal enclosures, raceways, and other metal parts that are likely to become energized. This section specifies the requirements for bonding these parts to the grounding system, ensuring that they are at or near ground potential. Surge protection is used to protect electrical equipment from transient overvoltages, such as those caused by lightning strikes or switching surges. Surge protective devices, or SPDs, are installed in electrical systems to divert surge currents to ground, preventing them from damaging sensitive equipment. NEC Section 230.67 requires surge protection for dwelling units, and Section 708.20 requires surge protection for critical operations power systems. It is important to select SPD that are properly rated for the voltage and current levels of the electrical system, and to install them in accordance with the manufacturer's instructions. Ground fault circuit interrupters, or GFCIs, are used to protect people from electrical shock hazards. GFCIs monitor the current flowing in the hot and neutral conductors of a circuit, and if there is a difference of 5 mA or more, the GFCI will trip, quickly disconnecting the circuit and preventing an electrical shock. NEC Section 210.8 requires GFCI protection for receptacles in certain locations, such as bathrooms, kitchens, and outdoor areas. It is important to install GFCIs in accordance with the NEC requirements and to test them regularly to ensure that they are functioning properly. Arc fault circuit interrupters, or FSIs, are used to protect against fires caused by arcing faults. Arcing faults are dangerous electrical faults that can generate high temperatures and ignite nearby combustible materials. FSIs monitor the current flowing in a circuit for the characteristics of an arcing fault, and if an arcing fault is detected, the FSI will trip, quickly disconnecting the circuit and preventing a fire. NEC Section 210.12 requires FSI protection for branch circuits that supply dwelling unit living areas, bedrooms, and other locations. It is important to install FSIs in accordance with the NEC requirements and to test them regularly to ensure that they are functioning properly. Electrical safety is paramount, and it is essential to follow all applicable codes and standards to ensure that electrical systems are installed and maintained safely. Always consult with a qualified electrician if you have any questions or concerns about electrical safety. The NEC provides a wealth of information and guidance on electrical safety, and it is important to stay up to date on the latest requirements. Firstly, understanding the fundamentals of electrical circuits, including voltage, current, and resistance, is crucial for ensuring electrical safety. Voltage is the electrical potential difference between 2 points measured in volts. Current is the flow of electrical charge, measured in amps. Resistance is the opposition to the flow of current measured in ohms. Secondly, the relationship between voltage, current, and resistance is described by Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms. This law is fundamental to understanding how electrical circuits work, and it can be used to calculate the voltage, current, or resistance in a circuit if the other two values are known. Thirdly, electrical power is the rate at which electrical energy is transferred, measured in watts. Power is calculated by multiplying voltage by current, or watts equals volts times amps. Understanding electrical power is important for selecting the appropriate size of conductors, circuit breakers, and other electrical components for a circuit. Fourthly, electrical circuits can be either series or parallel. In a series circuit, the components are connected in a single path, so the current is the same through all components. In a parallel circuit, the components are connected in multiple paths, so the voltage is the same across all components. Fifthly, electrical wiring is typically color-coded to indicate the purpose of each wire. In North America, the hot wire is typically black, the neutral wire is typically white, and the grounding wire is typically green or bare. It is important to follow the color code when wiring electrical circuits to ensure that the circuits are wired correctly and safely. Sixthly, electrical panels are used to distribute electrical power to various circuits in a building. The electrical panel contains circuit breakers or fuses that protect the circuits from overcurrents. It is important to label the circuit breakers or fuses in the electrical panel so that it is easy to identify which circuit each breaker or fuse controls. Seventhly, electrical receptacles, also known as outlets, are used to provide a convenient source of electrical power for appliances and other electrical devices. Receptacles are typically rated for 15 amps or 20 amps, and it is important to use the correct type of receptacle for the circuit. Eighthly, electrical switches are used to control the flow of electricity to lights and other electrical devices. Switches are typically rated for 15 amps or 20 amps, and it is important to use the correct type of switch for the circuit. Ninthly, lighting fixtures are used to provide illumination. Lighting fixtures are available in a wide variety of styles and sizes, and it is important to select the appropriate type of lighting fixture for the application. Tenthly, electrical appliances are devices that use electricity to perform a specific function. Electrical appliances are available in a wide variety of types, and it is important to use electrical appliances safely and in accordance with the manufacturer's instructions. Remember, electrical safety is paramount.